My name is Zaman and I'm a PhD student at University of Texas at Arlington. In this talk, I will present a new query language which is deeply embedded in Scala programming language. At first, I'll talk about the limitations of current query languages. Then I will present our query language DIQL, which stands for Data Intensive Query Language. Then I will describe our formal framework, which is based on monoid homomorphism. And finally, I will present a method for converting nested queries to joins. We are all familiar with programming environments for big data analysis, such as MapReduce, Spark, etc. They are all designed for large-scale data analysis on computer clusters, and they often work on raw data. They hide the details of distributed computing, and they also provide fault tolerance. Many of them provide functional programming style API, which consists of powerful higher-order operations, which allows to build complex applications. Using functional programming style prevents interference among parallel tasks, which is important to achieve data parallelism. However, some programmers are not familiar with functional programming. In addition to specification, they also have to provide low-level details specific to optimization, which complicates programming. Most importantly, there are a lot of competing big data platforms right now. For example, MapReduce, Spark, Flink, Storm, etc. At this point, it's hard to tell which is going to be popular in the near future. So one solution can be to use a query language which is independent of underlying platform instead of using one particular big data platform, and build a query system which will translate the query to a particular big data platform. Current query languages for big data platforms are based on relational models. They are subsets of SQL. However, the raw data can be often nested. They are not normalized. So that makes a relational model not a good choice for big data analysis. And the current query languages also have limited syntax to operate on data collections using only simple join and group by. They also have limited support for nested collections and hierarchical data. They also can't express complex data analysis tasks that needs iteration. For example, page rank, clustering, etc. They also have different syntax for in-memory and distributed collections. So we have to use different syntax for each one of them. So the design goal of our query language DIQL was to completely avoid impedance mismatch. To avoid impedance mismatch in database community basically means the query language is deeply embedded in the host programming language, such that the values from the programming language can be used inside the queries, and the result of the query can be passed back to the programming language. In order to do that, the data model for programming language and query must be equivalent. We also know that the queries must work on special collections. In our case, it is distributed collections, which has very special semantics that are not part of the core programming language model. We also want to use the same syntax for in-memory and distributed collections. So of course, we want to treat the distributed collection differently, because distributed collections should be processed using higher order operations of the particular big data platform. We also don't want to introduce null values, because that complicates our formal framework. On the other hand, SQL uses three-value logic, which is also complicated. Another reason is that the programming language don't provide standard way to treat nulls. So if you want to make a call to user-defined function from our query, we have to make sure that we remove the null values before we make that call. So that means we can't do outer join the way SQL does outer join. However, what we have is the same functionality, but without nulls. So our query language DIQL is SQL-like, but it has different semantics. It is deeply embedded in Scala, and it's designed to support multiple Scala-based API. Currently, it supports Spark, Flink, and Twitter's cascading scaling. It can uniformly work on both in-memory and distributed collections. And most importantly, it doesn't have any impedance mismatch. So we can mix SQL-like code with Scala code with SQL-like query syntax. So and also we can use any Scala pattern. We can access any Scala variable, and we can use any core Scala code. We can also use Scala library, any core Scala library, and even user-defined function. It has compositional semantics, which is based on monoid homomorphism. So our query processor translates and optimizes queries to Java bytecode at compile time using Scala's compile time reflection and macros. So everything is done at compile time. So one might ask, what about the cost-based optimizations that are based on runtime statistics? Well, that can also be done by letting the optimizer pick a small number of query plans at compile time and generate conditional code. The condition would be to check the statistical information at runtime and choose plan based on those conditions. The DI query syntax is SQL-like, but it's more uniform. We can use any kind of Scala pattern, we can use any kind of Scala expression. So if you want to traverse the data set, in a query, we use the qualifier Q. And we have some domain E which must return a data set. And we have also pattern P which traverses the data set one element of a time. So every single time the pattern P is matched with element E, the pattern variable inside the pattern P is bound to that element E. And we have also another qualifier to traverse over a small data set which has a very similar syntax. In this case, the data set should be small enough to fit in worker's memory. This is usually done by broadcasting the data set to the worker nodes. The third kind of qualifier is called binding. Here, expression P returns the value and the pattern P is bound to that value. The expression can be any kind of Scala expression as long as it doesn't have any side effects. So the select syntax looks like this, where the square brackets means optional. So in the query, we traverse the data set using the qualifiers Q, as I have discussed previously. And after that, optional condition E in the void clause is executed. And then group by is executed. And here the expression E is basically group by key, and the pattern P contains the variables bound to that group by key. Having has the same functionality as in SQL, which is basically the E in having clause is basically the condition to be checked after a group execution of group by for every group. In the end, we have optional sorting using order by. We also provide another expression called aggregation, and we provide a monoid such as plus to do the aggregation, which is evaluated over a data set. It is basically applied pairwise to all the elements in the data set using that monoid. The group by semantics in DIQL is different from the semantics used in SQL because the aggregation is completely detached from group by. Group by construct nested collections. So if we want to do aggregations, we do the aggregations on those collections. Pattern variables are very important for group by because group by lifts every pattern variables to a bag of values. So we can have groups for every different pattern variable and every different group by key. So this allows us to have multiple groups for every different pattern variables. So let's see an example of how group by works. So this is an example of a matrix multiplication for sparse matrices. And each matrix is represented by this data set of triples where V is the value and I and J are row and column indices. So we want to multiply matrix X and Y, which are sparse. And the result of the matrix multiplication is basically the summation of the products over the index K. To explain in detail, matrix X is represented by Xik, and matrix Y is represented by Yk_J. And new value Z is calculated. Z is basically the product of X and Y. And at the same time, we enforce that K must be equal to K underscore. And then finally, we group by I and J. So in this case, the pattern, all the pattern variables, including Z, is lifted to back, except I and J, because they have only one value for each one of them. So when we do the query, we have multiple values in Z, and then finally we do the aggregation. In this case, we do the summation of all the products that we got for indices I and J. And then we get, after the aggregation, we get one entry of the resultant matrix. As I have mentioned earlier, we don't have any null values. So our outer join is different from the SQL outer join. So let's see an example of that. So The problem here is to see the name of all the customer names in the output whose account is greater than equal to the sum of all the order prices the customer has placed. And we also want to see the name of the customers if the customer didn't order anything at all. So in SQL, what we do is that we outer join the customer table with the order table, and then we group by customer ID. And then we check the condition of if the account is greater than equal to sum of all the order prices of the customer, and we also check if the order price is null. That means the customer didn't order anything, so we can see the name of the customer in the output. We can simulate the same thing in DIQL using a nested query. So at first we select the name of the customer from the customer table to make sure that we see the name of the customers in the output, and then we check if the customer account is greater than equal to the sum of all the order prices. We sum all of the order prices using the inner query like this. We select the price from the order table where the customer ID is equal. So we sum up all the order prices and then we check the condition. So one might ask, what if the customer didn't order anything? In that case, this inner query will return an empty set. And if we do plus over an empty set, we get 0. So which makes this condition to be evaluated to be true. And then we see the name of the customer in the output result. So I have also mentioned that we can mix any Scala code with the query syntax, and we do that using macros. In this case, Q is a macros for query. The problem in this example we are solving is finding the neighbors of all the nodes in a graph. And each node is defined by using this pair where ID is the node ID and the second element is the list of its adjacent nodes. And the input file is graph.txt, which contains the specification of the graph in a comma-separated file. So we construct graph out of every line of graph.txt. We construct node out of every line of graph.txt, and then we match this pattern with that node to get the information about the neighbors of each node. And it's stored in A. And then we pattern match again with nodes to get the information about the neighbors of each node, and then we make sure that y is equal to A. So which gets us the information about the neighbors of the node X, for example. So basically what we do is we join each node X with its neighbors, and then we group by X to get get the neighbors of all the nodes. So the formal basis of DIQL is monoid homomorphism. Associated with important to achieve data parallelism, because in data parallelism we divide the data into multiple partitions, and then we do computations on those partitions, and then we combine the result. So in order to make the result independent of the way how we divide the data and then we combine the results, the computation must be associative. So that's why we need monoid homomorphism to express data parallel operations. The basis of monoid homomorphism is monoid, which has an associative merge function with an identity. We also have a spatial monoid called collection monoid, which has a unit function. The unit function gets a value and then construct a singleton collection. For example, this is a singleton collection. This is a collection monoid for bags, which consists of a bag union, empty bag, and a function which leaves value to a singleton bag. A monoid homomorphism can map collection monoid to a monoid, which basically captures data parallelism. For example, H is a monoid homomorphism which is applied to partitions P1 to Pn, which is equal to the computation applied to partition P1 to Pn, and then merged with, combined using some monoid. Monoid algebra consists of very few algebraic operations. The most important one is flat map. In flat map, we apply a function to each element in the data set, and then we get the result, which is merged into only one bag. For example, here, this function, which is basically an increment of each element, is applied to this bag, and we get the result incremented by 1. And the monad for flap map is called bag union. In group by, it has as input key value pairs, and then we get the result as key value map, where where the key should be unique, and the value is basically bag, which is correspond to each ID. So as you can see, one had the elements A, C, and D, and then we get the result accordingly. The monad for group by is called indexed set union. Order by is similar to group by, but at the same time it also sorts the output according to the group by key, according to the unique IDs. So here we also have key value pairs in the input, and we get key value map where the value is the bag correspond to each unique ID. And the monad for order by is called merge sort list. Co-group is basically a join, and it can also capture outer join. It gets key value pairs, and it generates key value map where the value is, in this case, has two bags. The first bag corresponds to the first data set, and the second bag corresponds to the second data set. So as you can see in this example, in the first data set, the ID 1 had the elements A and C, so the first bag contains A and C. And for the second data set, the unique ID had 5, and we have separate bag for that value in the output. Reduce is basically aggregation, and we provide monoids such as plus to do the aggregation. And this it is usually applied pairwise to all the elements in the data set using that monoid. For example, we can see that plus is applied to all the elements, and we get the result without. We have developed a very general algorithm to unnest the queries. For example, if we have nested flat map like this in our query, where G can be anything, for example, flat map, group by, etc. This G can be converted to co-group over input X and Y if this H function can be converted. So basically we need to find keys K1 and K2 such that this H is 0 only when the keys K1 and K2 are different. So we get the results for K1 for X and K2 for Y, and then we join the results over the keys K1 and K2. This co-group is usually applied using distributed partition join or broadcast join. In broadcast join, the small data set is broadcasted over to the partitions to be joined with the partitions of the partitions of the larger data set. To conclude, our query language DIQL is based on compile time code generation. It uses Scala's compile time reflection and macros. Currently, it is implemented on Spark, Flink, and Twitter's cascading scalding. And we also provide a debugger based on provenance. So that's all from me. Thank you all for your patient hearing. Thank you.